Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but I really need some new equipment. Well, time to make it rain.
Damn. Yeah. Yeah. Yeah.
Woo! Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
All right, everybody. I think we are live.
Hello. Hi, everybody.
Hello. The
Welcome.
first and foremost, yeah, sorry to cut you off there.
No.
First and foremost is somebody in chat, if you would be so kind, type something that says, I hear the words that you are speaking.
Yeah, always want to do an audio check
That's
just
right.
to make sure that everyone can hear us. There's multiple different things with Zoom and video that we always want to make sure people can hear us. So
That's right.
we see some questions in chat. So Pavel and Explore South Korea, please let us know if you can hear us.
That's right. Why don't you
And I'll just
kick us off here? And,
yeah, let me just read the boilerplate. Sort of say, welcome everybody to Pine Research's live stream. Ask us anything about electrochemistry live stream. I'm Dr. Alex Peroff. I'm with my co-host, Dr. Neil Spinner, and our goal is to answer as many questions as we possibly can during this live stream. We get a lot of questions via email, through webinars, on YouTube videos, and sometimes we can't always just type in whatever the answer is or what the best solution is. Sometimes it requires a little bit more time to answer and a little bit more depth, which is what these live streams are for. So first and foremost, type in any question that you have in chat. We usually give a little bit of preference to members. We have YouTube members, and thank you all YouTube members for joining us and supporting us, helping us make this content. Note that we are using Zoom as the recording platform. So Zoom tends to have, we have found, a 20-second delay between what you see in front of you and then what actually gets typed into the chat. So if you type something and you don't hear immediately from us, don't be alarmed. It's just perhaps a small, short delay. You can ask us any questions at all. If you're watching this video after the live stream, we usually have it posted to YouTube. We're going to put the questions in the description below. So if you couldn't make it to this episode, you want to listen to this again, within a few days over the weekend, we'll have some time to go through all the questions, write it out in the description below if you're watching this after the live stream. And then we estimate that this live stream will be about 1 to 2 hours, depending on how many questions. Maybe we'll go a little bit further. Depends on the level of engagement that we get. And lastly, I think there are no, like, electrochemistry is a very hard subject. So there are no stupid questions. You can ask us some basic questions. The more specific question you have, the better off it'll be when we come to answering it. And lastly, before we begin, we're going to apologize in advance if we mispronounce your name when trying to address your question.
yeah, we're going to mispronounce everybody's name. And it's not intentional. We're just not good at that. So it is what it is. Before we see, there are some that are in the chat. I do see some. Thanks. Actually, Lazy Sniper. There were some from earlier. For your information, it's the way this sort of works logistically. I know it's not that interesting here, but we make the scheduled event so you could see that this event was coming. And just this exact one that you're watching right now is not the same one that was scheduled. So when you typed your questions in before, for some reason they like disappeared. That being said, I did take note of them because I wanted to answer. There were two people who asked questions. So Lazy Sniper, you are one of them. And there was another, and I apologize, I don't remember the name, and I don't remember who asked which question. But I did note them down. So I will try to cover those first, because those were asked sometime in the past 6-7 hours or longer. So apologies that I don't have the name or the exact questions, but here's the first, I suppose. And Alex, I saw these, so you're gotta go with me here.
I'm gonna trust you on this.
Yeah, you're trusting me. That's your first mistake. So okay. So the first question, and again, Lazy, this might be yours. I don't remember. If not, it was the other person who asked a question. It was a question about a zinc battery. So the question was something, and again, I didn't copy the exact text, so my apologies, but just from my memory was that the person had a zinc battery. They had a certain size. It was like some rectangular, like 1 millimeter thick plate of zinc as the anode, and the cathode was a stainless steel sheet. They were measuring 1.03 volts. And again, just I'm going by somewhat memory here, what I was able to remember and note down. Something about how they could maybe simplify the design, or okay, so you're the one with the battery. So please feel free to type some clarifications about exactly what you were asking, because I don't 100% remember. Something about how you can simplify the design, or like, you know, about the just some general questions, I guess, about the you know, measured voltage that you're getting, or at least the output. So the first thing that I wanted to sort of do here, I'm going to use this really strange resource. It's called Wikipedia. So first, what I want to do, just to sort of illustrate for you, I'm going to share. Which one is it? This one. Yeah. So first of all, if you can see here, this is just the Wikipedia of standard potentials. So just to sort of explain to you, and maybe to others, if there's interest here, you're getting 1.03 volts. Now, this is a tricky thing here. So when you have a battery or a fuel cell, basically the potential you get, or the voltage really, is effectively the cathode minus the anode potential, like half reactions. Okay. Now your anode is zinc. And so zinc is about minus 0.7. It's up here somewhere. So this is probably the reaction that's going on at the anode. Okay. This one that I've sort of just highlighted here, zinc, it's the, and they're written as standard reductions. And so it's a minus. And so this is why you have a positive potential, because you have cathode minus anodes. You have minus a negative 0.7, whatever. Okay. So you're basically adding 0.7 volts for the zinc part. Now the cathode, here's the tricky thing. And this is why I'm not 100% sure, because stainless steel wouldn't really be my choice probably for the other one. Typically you think of like copper zinc batteries, the most sort of, I don't know, famous example that people do in like classes for learning about stuff like that, these kinds of things. And the reason for that is that copper is, where is it? It's over here, I guess. Typically we do this, but copper has plus 300 millivolts or so, and zinc is minus. So when you put copper and zinc together, makes a nice you know, whatever that is, 1 volt, one some odd volt, you know, when you subtract 0.3 minus a negative 0.7. Okay. With stainless steel, it's a little tricky, right? Stainless steel is an alloy that has a lot of stuff in it. Now, its primary component is iron. The tricky thing is, I mean, we could try to, like, what is the reaction at the cathode if your other plate is stainless steel, right? There's chromium, there's iron, there might be a little copper. So maybe it's this copper reaction, and that's why you're getting about 1 volt. If it's iron, I'm skeptical that it's just pure iron, because if you see, there's a lot of different possibilities for iron reaction. So like a 3 electron, that's probably less likely. But if it were this one, you would not expect to get 1 volt. And then I think like the iron 2+, I think it's all the way up here somewhere. It's more of a reaction you'd see at the anode, not the cathode. So anyway, for example, is if you had this, you would expect as your cathode minus 0.44 plus 0.7. So you would only expect a cell voltage of about 300, and you're getting 1 volt, 300 millivolts. So my point of this is twofold. The first is that, so I'm looking at your comment. I'm only applying for a patent currently, so I'm being careful. Okay, no problem. It's fine if you can't really specify much more. What I just wanted to do was to kind of make the distinction between the voltage you're getting and the current or the stuff you can draw from the battery. Okay, so the potential or the voltage of your battery is going to be dependent on this table, whatever the effective, if you will, thing or half reaction or combination of half reactions, I guess, whatever is happening at the cathode has some potential associated with it. Subtracting the zinc side is going to give you your voltage. But the current or the power that you can draw from that battery is going to be dependent on like how much of that stuff you have. So your question was somewhat related, if I recall, to, something like, well, can I make a smaller zinc anode or whatever? This is why, in short, people do stuff like nanoparticles, or they increase the surface area, right? They're getting more of the material because the potential of a nanogram of copper and zinc is the same as a kilogram of copper and zinc. It's just the potential. That's just the voltage between those two, which is determined by these standard reactions, right? But the current that you can get will be determined by how much is there and how effectively your cell is constructed or whatever. So I suspect, again, without being able to give me more information, because if you're doing a patent thing, I get that. So that's fine. My point is that if you're trying to do something with like steel, I suspect there's going to be some trickiness as it relates to what exactly is the reaction at the other side, and how can you predictably and reliably determine what the voltage is? Because it's an alloy. It's not like one material. How much electrolyte is ideal in concentration? For a battery kind of system, as high as you can go. You
want the lowest resistance.
Right? Yeah, exactly. You want to have a high, what would you call it, like ionic mobility, all that kind of stuff, right? You want to have people, for example, like with the most common example of like a PEM fuel cell, you saturate usually the Nafion membrane in sulfuric acid, like 1 molar or 2 molar sulfuric acid overnight. So it's like super drenched. That's the bridge between anode and cathode, where your ionic, communication transport happens. You don't want that to be limiting at all. So in general, the answer to that is as high as possible. Mm-hmm. Okay. That might be as much as I can kind of help. I'm glad that if you found it helpful there, and certainly without, you're doing proprietary kinds of things, so you probably can't give me more information. I totally understand that. The second question, again, before we'll get to some of the ones that are just today, Kempur, I think you're the person who asked the second question, which I'm just going to look at your comments in here. AC electricity for electrolysis. Okay, this is not. So the question that was in, and maybe this wasn't you, I think it was, sodium sulfate electrolyzed in water, something about ChatGPT. Interesting. Okay. So this might be related, but in any case, the question that I think it was you, because I do see that you're a member. The question was related to an anode and a cathode. Unclear if this is like a flow battery or a fuel cell or something. The question was related to adding like a steel plate as the membrane or something like that. And so what I just wanted to say about that was you can do that. The concerns are that, for example, if you have a membrane for a battery, for a fuel cell or anything, typically the membrane serves the purpose of allowing ions to pass and not electrons, right? It's an electrical insulator, right? I think we had this question last week, some related, kind of a inquiry last week. The things to be concerned about are like, if you have like, let me draw what I mean. rather than like
Sure.
point at the screen with my finger, which
Yeah.
doesn't really help here. So
And also for you all, we see that you're asking us to answer some questions with repeated comments. We will get to you.
yeah.
Just we ask that you be patient as we try to provide a very complete an answer as we can.
Hang tight, everybody.
Yeah.
We will try to get to everything.
Yeah.
So let's say you have some separated cell here and you have your membrane in between, and you want this membrane here to be, metal instead. This is your membrane. Well, if you have anode here, cathode here, and it's some sort of divided cell, and you have electrolyte or whatever. Okay, well, I don't know the specifics of this material. Typically, this material has to allow, ions of some kind, positive or negative, to pass through, right? One way or the other. Okay. If your metal has some sort of porosity, something like that, then I suppose it could work just fine. But I don't know the specifics of that. The problems that you would run into potentially are if you have a battery or a fuel cell where you have everything physically pressed together, right? That's where the membrane is very critical here, right? This let's say this is, Nafion, is that right? I should probably use the typing thing again. Every time I start writing clumsily here. And this is my anode and my cathode. And often what you do is you press them in, and so they're physically touching either side of the membrane, right? Well, this only works because Nafion is electrically insulating, right? If you put a piece of metal here, you've just shorted the whole system, right? Normally you're connecting this to some load or whatever, but if the anode and the cathode directly touch each other, you just shorted the whole thing. No porosity. Okay. So there is without porosity, I'm not positive how this works. Now, there's some thought. This is similar to the concept of leakless electrodes, reference electrodes. I'm kind of getting a little off on a tangent. I promise I'll wrap this up quickly. I've had this kind of discussion before with a friend of mine who's a professor. It's like, is there some way, like the point of this membrane that's separating the thing is it separates the two compartments, right? But it has to have a way to electrically communicate, right? A membrane does that by allowing ions to physically move through. So there's a charge moving through this membrane one way or the other. Now, with just a metal plate, there's no porosity, like you say. So the only way physically for charge to move is if an electron somehow moves. But how exactly does that happen? You have to have some redox process on either side, maybe some sort of additional couple. Does that need to be driven with a separate circuit here? And I don't know. I don't know the answer to this. Like, will a reaction spontaneously happen on both sides of this metal plate to facilitate the transport? I think if you just put a metal plate, my suspicion is that you will not get a reaction to spontaneously work just connecting anode and cathode. That's my guess. I may be wrong. Well, I mean, do you think it would something would happen?
There is something called a bipolar electrode.
Okay, so maybe that's an exception. Is that the plate you're talking about with the bipolar?
It's like you have like just almost a bare piece of metal just in solution.
Yeah.
And then you have basically an anode and a cathode on both sides. And when you apply a potential between anode and cathode, I imagine it's got to be pretty high.
Yeah.
But the metal feels that electric field,
right,
and will polarize the ends, and then you can do electrochemistry that way.
So the field, basically, if there's a field between, I mean, there's going to be an electric field generated between the anode and cathode, no matter what. No electrical connection. Been getting interesting results. No reaction at the cathode side. Heavy reaction on the anode side.
Oh, that's strange.
That's interesting. Yeah, to me, that feels like the potentiostat or whatever power source you're using is like really heavily trying to make it happen, and it's like not really quite able to do it, I guess, something like that. Lazy sniper. I'm gonna put the link. It's just the Wikipedia page for
electrode
standard potentials. Let me put the link in the chat for you. I can just
it's
the Wikipedia
easy.
link. Here's the link. I've used this. I mean, I'm not too proud to use Wikipedia. It's really great. I highly recommend it just in general.
Yeah. What's strange about, like, you get a reaction on one side and no reaction on the other side. Like, there needs to be charge balance.
Yeah.
Somewhere.
So to me, it feels like, on the plate. Yeah, this is a very strange. It feels like when you, something about the electric field is inducing stuff heavily. That's really interesting. I guess a more in-depth conversation, which, just for the sake of time, and there's a lot of other questions, I don't want to get too more into it, but a more, discussion. If we had this, I would say, why exactly are you using what's the impetus to use? Maybe you can't find a suitable membrane. I get that. Maybe that might be why. So there's some things that could be related. But yeah, that's a bit of a strange phenomenon here. But I think we're gonna try to leave it there just so we can make sure we get to the camera move.
Camera may have moved just a little bit.
Yeah, I'm gonna move it here. You get some of the here.
So now we tend to I see that you want to get to some cyclic voltammetry analysis. But what we try to answer, we prioritize member questions first. And Israel Martinez asks, what's the difference between a 2.2 electrode versus 3 electrode system in order to get impedance data? Thanks. So I think this is probably one of our favorite types of questions, because we struggled with understanding what exactly is EIS doing, and you can comment along. Let me see.
You're on the other screen.
I'm on the other screen, which is fine. So I'm gonna annotate and hopefully help you, at least from my perspective, understand a little bit about what might be happening. So in a 3, so there's like a 2 in the 3 electrode system. And whenever we think about impedance, we're always thinking about, like, okay, we have, like, some resistance, and then you're used to seeing stuff like this, just whatever the circuit may be. Okay. All right. And then, and you usually draw this as like the circuit model, but the question is, what exactly is this? And what exactly is this, right? What's connected on each side? We usually don't even think about it that much.
Those are question marks, by the way.
Those are question marks. Sorry, I might not be that great. Like a little question mark.
Says the guy who also can't draw.
I can't draw.
I can't draw. Definitely, that's fine.
So in a 2 electrode system, this is really easy. You can understand this very easily. It's like, this is like working electrode. Actually, I draw it this way. I draw a working electrode. Let me type, because typing is
yeah. So you're learning from my
mistakes. I'm learning from your mistakes. That
typing is way better. Yeah, take
this. Sorry.
Here, move this over.
We're adjusting. Minor adjustment. So we usually refer to this as, like, this is the working electrode, and then we have the and on this side we have the counter / reference electrodes. Actually, I'll spell that out. Counter reference. And this is shorted. This is the 2 electrode system that you're asking about, Israel. So this makes sense for a 2 electrode system when you're doing EIS. That makes sense. 2 electrode system, very easy to understand what's happening. You're applying and measuring a potential between these 2 things. It's just a sine wave. Now, the 3 electrode system is more complicated because counter and reference are not connected anymore. So what ends up happening is you need to understand that counter and reference become decoupled in these 2 ways. And that is that the counter electrode drives current, and the reference electrode measures potential. No, let's make this a little bit wider so it just measures potential. And this is no longer part of the fact that there's just one node is no longer part of the circuit that we model when doing EIS. Now, what this actually means physically is kind of tricky. So normally your counter electrode, I'm just going to draw this out over here for space. The counter electrode has some resistance associated with it. It also has its own like Randall circuit, sort of say. So it has a resistor, and it also has a capacitor. It's got some other stuff. So the current that you measure when you're looking at impedance, and that's V over I, just generally speaking, like impedance, I'm just doing the very generalized form. Nope, because that looks like a 2 with a line as opposed to a Z. There we go. Z.
There we go.
For the impedance, right? So that's what we're measuring. Where'd my mouse go? Okay. Right. So that's, I know this looks so weird. I'm sorry, everybody, but Israel, if you're still with us, hopefully this is making sense. So the impedance that's measured contains these two things. It contains a voltage and it contains a current. The current that you measure when doing impedance contains all this information from the counter electrode. So counter is here. I'm going to put CTR here. But the reference, the potential that you measure might be here. This might just be, reference is just measured here. So the potential may actually just be measured from this point to the working, but the current information is actually from this point to the working. So that is kind of the weird, strange thing about impedance data, is that the current data contains, right, magnitude and phase of all this other stuff through the solution. And the reference is actually just potential between reference and working. And that's what impedance data is made up of. So Israel, I hope that makes sense. Leave us a comment in the chat if that kind of makes sense. That's my best understanding, at least, about EIS between 2 and 3 electrode systems, how to think about that. I don't know if you have any.
Yeah, I mean,
I'm gonna clear this.
Yeah, that's fine. Yeah, I mean, it's tricky. It's always hiding behind this thing.
Oh, okay.
It's like hiding.
Sorry.
Yeah.
Okay. All right. We're back.
I was like, what's it?
Okay.
Yeah. The last thing I'll say about that, which Alex did that was more, thorough than what I'll say. All I'll say is that the main difference, really, honestly, is just that with a 3 electrode system, you're not measuring voltage where you're measuring current. You're just not, right? Not necessarily. So, and then the other thing that I'll say about it, which is one of these interesting fundamental things about it, as it relates to people who are doing batteries and fuel cells versus 3 electrode, aqueous phase and non-aqueous, whatever, is that when you do 3 electrode impedance, the information you get is about the working electrode only. When you do 2 electrode impedance, you are getting information from both anode and cathode. So, yeah. It's a bit, I'm not going to talk about it more. It's pretty complicated, kind of a electrical engineering phenomenon. You and I spent we spent like 3 hours one day with our electrical engineer colleague trying to figure this out and think through exactly what's happening and why and what the potentiostat is doing. I mean, we work for a company that makes potentiostats, and we're still often like, what's exactly happening? Yeah. We're learning about this a lot too. The point is that, like, when someone does impedance on a battery and they say, well, this part's the anode, this part's the cathode, and this part's the SEI, and blah, blah, blah. That's because it's a 2 electrode system. And so you are actually fundamentally getting information about both sides of your impedance thing. When you have a 3 electrode system, you have a working and a counter, but then you have a reference over here. That the reference basically makes it so that you're not measuring the counter electrode. You're not getting information implicitly on that counter electrode. It's basically not part of your impedance that you're only getting. So that's good or bad. It depends, right? If that counter electrode is a cathode or an anode that you want to measure, you're not getting that information if you're doing 3-electrode, unless you have a different kind of system. But most of the time, we don't really want to measure the counter electrode. So that's a good thing. We just want to measure the working electrode. We want to get that kind of information. That's what a 3-electrode setup allows us to do. I hope that answers that question as relatively succinctly as we can.
All right. That seems to like it. Okay.
Let's see. So we'll try to go from the start of the session here. Pavel says, could you look at my EIS? No. Next question.
We just don't have your data.
We don't have your data.
I mean, we don't like it.
So the answer is maybe.
Maybe.
Yeah, I mean, this is a good forum for us to try to answer questions, except that we have the ability to give you visual things. You don't have the ability to give us visual things. It's a little tricky. Can you type our email in? Yeah. I'll put, Alex is going to type in like our company email address. You can send us an email at that address if you have specific questions or data, and we can possibly give you give you some help with stuff on specifically, or we can do consulting kinds of, if there's a lot of information you wanted to work out, or you wanted to maybe have a several hour kind of a discussion or consultation with one of us about some of your data, we can provide those kinds of consultation services, so we can discuss that offline. But without knowing your data or seeing it, obviously in this right now, I can't do very much. So we'll take that offline. Please email us, and we'll get back to you when we can. Go. Yeah. Go ahead.
Oh no, I was just gonna go next question. Just kindly tell us about chronopotentiometry and how we measure electrical impedance. All right, I'm assuming that's supposed to be electrochemical impedance spectroscopy. Thank you. That's from Explore South Korea. Well, in short, chronopotentiometry is a galvanostatic technique. That means that we're controlling the current and allowing the potential to change. And that's all that experiment is. You say, oh, I want to apply, say, 5 milliamps of current, and then we'll see how does the potential change as a function of time. So chronoamperometry, chronopotentiometry, chrono refers to time, and then amperometry refers to current. So that's measuring current as a function of time. Chronopotentiometry, measuring potential as a function of time.
Words mean
stuff. And measure electrochemical impedance spectroscopy. I mean, you have usually a potentiostat that can do EIS with a 3-electrode system. And then you would set up some just basic parameters. So I don't know if you want to show them just in aftermath.
Yeah. So for example, let me share it.
We're just going to share screen.
Yeah. I mean, how you measure electrochemical impedance spectroscopy is quite a loaded question.
Yeah.
To be honest, you get a system ready, right? Whatever your system is, or I guess, and you connect it to your potentiostat, and you get into your software and you choose galvanostatic or potentiostatic, similar to what Alex just talked about. Chronopotentiometry is when it's actually sort of opposite here word wise, but anyway, that's a galvanostatic, as he said, type of process where you're controlling the current, measuring the potential. That would be like galvanostatic impedance, where you're controlling the current, which is the sine waves, and measuring the resulting potential, or vice versa, which would be potentiostatic impedance. It's more common, potentiostatic impedance, that is, where you set some baseline. Sometimes it's just at OCP, sometimes it's at some different potential, whatever you want, and then you do sine waves at various frequencies, and you measure the response. And then you get, there's a lot more to it, a lot of different analyses, of course, but that's the most basic answer to how you measure impedance, I suppose.
Yeah, I mean, literally, like, you can use the potentiostat, but if you have a sine wave generator that has an oscillating sine wave at a frequency, you could literally hook it up to your cell, the potential, and you just measure the current. You get these two waves, and then you start taking some ratios between them, and that's EIS.
Yeah. Okay. Let's move right along here. Let's see. So Bia says,
lithium as
Yeah, so the basic question, when an electron goes to anode in a sodium ion battery during charging, an electron goes into the anode in the sodium ion battery during charging. Okay. Why and how does it go back to the cathode during discharging? Is there any force or what? Yeah. I mean, the force is the load, the potentiostat, the phone that you're using, the whatever thing that's drawing it out. Okay. So a battery is a device that stores charge, which means that it fundamentally is very stable when not being perturbed, right? Okay. So first of all, you have to answer, how does that electron go into the anode, right? And so what you're referring to is that there's a reduction process happening at the anode. That is the process of charging a battery. You're charging your battery when the anode is having a reduction process. You're basically loading it up with something. You're loading the anode with lithium ions or sodium ions or whatever, right? That is the charging process. Well, something had to push the electron there because that doesn't happen spontaneously. You have to plug your phone into the wall to charge it, your laptop, your whatever, to charge it. Okay. So something pushed it in. So then something has to change the voltage of the battery or start drawing power from it. And so that electron has to travel through some external circuit. Now that external circuit is a potentiostat, or it's literally your phone while you're scrolling Instagram or whatever. It's always my example. I don't know why I always go to Instagram. I don't even have Instagram. But I was just, it's the first one that comes to mind for some reason. Anyway, I'm not sure what it says about me, but but the point is that action, right? That whatever I'm talking about here is something that is drawing power, which is current, it's electricity. So that is a process that causes the electron to then go from anode to cathode. And that's an oxidation at the anode. It's a reduction at the cathode. That is a discharging process. And so, I think that's your answer.
Yeah. I guess I've thought about, like, not that I've done very much battery science, but it's almost like there's kind of a, like, if you have the chemical system in equilibrium, nothing's going to really happen.
Yeah.
And charging it is like moving it out of a state of equilibrium.
Both are charging and discharging.
Charging and yeah, right.
Yeah.
And so the discharging, when it's actually doing the work, it's like there's a force. They want to do this. It's only when you connect it to the device that now has a path for that charge. It's like, and the water in the hose. You could have all the pressure buildup in the hose, but until you unleash the nozzle, nothing's gonna. It
has nowhere to go. Yeah, exactly. In some sense, a battery is interesting in that way because you have to provide it an impetus to both charge or discharge. One is thermodynamically favored and one is not, right? It's not thermodynamically favored to charge something that you have to put energy into it so that you can get energy out later, right? And but the nice, that's what a battery is, like, useful for, is that it doesn't just spontaneously give up energy, it stores it until you provide it impetus,
load.
Load.
It can go through a circuit.
Exactly.
All right. I think Fika, you've been asking a lot about cyclic voltammetry. So you want us to help you with guiding you through how to plot a graph of a cyclic voltammogram. I think this is about whether you know that your CV data is correct or not. Leave us a comment if you're still there. But we will now try to provide at least a little bit of guidance relatively quickly on CV analysis. Remember, some of this stuff is CV, like you could talk for an hour on cyclic voltammetry basics. So I'll try to make this relatively brief. And if you have very more specific questions, please let us know. But just very brief cyclic voltammetry. And while I make sure I'm doing this right. Okay. So in a cyclic voltammetry experiment and CV analysis, you typically have first off, what you're doing is if you have voltage versus time, you are applying some kind of triangular potential waveform, a linear sweep. And what you're measuring is the current as a function of the potential or the voltage. And what you get is some kind of plot that generally looks like this. Trying to do this as carefully as I
That's
can.
very good.
I'm doing it
Yeah.
super carefully, but it's also because of my positioning here.
That's so good.
I guess. Well, all
That's
right,
really impressive.
thank you.
It's like that's like perfect
guy-
60 millivolt split
Yeah,
peak.
this like stupid.
I mean, up there looks terrible.
Yeah, this
but
looks
the duct
terrible.
looks great.
This is almost like a amperometric,
actually
like
looked like-
chronoamperometry experiment. We're measuring charge over time.
it looks
So,
like
yeah,
a
it looks bad.
mountain that's tipping over.
Yeah, that doesn't look good. This is garbage. But this is the kind of response that you get, and I just want to make sure still there. I don't know if you're still there or not. Let me just. Well, actually, I'll just continue a little briefly with the analysis. But this represents, say, an oxidation reduction reaction. So when you get this current response here, this is literally at the electrode surface. So if this is an electrode, your working electrode, some molecule in solution is losing electrons. So this is an oxidation. So the molecule is donating an electron to the electrode surface. That's what's happening. And as a result, because current is moving, you see a current. Electrons are moving, you see a current. This response is due to diffusion. All right, so it's just based on the diffusion of molecules at the electrode surface. Eventually, the current starts to decrease down in this region here, and basically, it's just because there are less of these molecules around. That's just like, this guy is oxidized. This guy's oxidized. It takes time for like a new molecule to diffuse towards the electrode surface. So the current starts to decrease. At this point, we switch the potential and we're scanning backwards. So that's the other direction. And eventually, as we're scanning, we reach a potential where it's more thermodynamically favorable for the electron to go back into the oxidized form of the molecule. So any of the oxidized form of the molecule that's here is going to get reduced. And that's why you see this current on the bottom. And then eventually, again, it gets depleted and the current goes from being negative to going back to like a positive or neutral value. There's a few other things. There's things like electrical double layer that forms. There's data. I mean, the half potential is indicative of the thermodynamic potential for the redox reaction. Those are some of the useful things you get with it. We have a video on our YouTube channel about just an introduction to cyclic voltammetry.
Yeah, you should link that after this.
And I'll link that after this. But that goes into more detail about cyclic voltammetry analysis. So hopefully that was helpful.
Yeah.
And
I want to answer the next one while you get the link here.
Okay.
Oh yeah, you had to
So
do
do
that.
you
Yeah.
need to-
No, I can answer it without. You can use the keyboard.
Yeah.
So I wanted to give this one was another member, Race. Thank you very much
Race.
for being a member. Your question was, how do solution resistance, charge transfer resistance, and double layer capacitance change as a function of state of charge and as the cell ages? Thank you. So in theory, now in practice, everything changes all the time because electrochemistry is a pain and nothing ever works the way it's supposed to. But in theory, so as like a battery ages or gets used or grows older or whatever, solution resistance in theory shouldn't really change much, although as I said, it will ever so slightly, but in general, it shouldn't change much. Charge transfer resistance will probably increase because it becomes less effective, which means that there's higher impedance, higher resistance for doing the charging and discharging processes. And the double layer capacitance will, I guess it depends. If your material starts to, it depends on the cell. It depends on this. If you're talking about a fuel cell, if you're talking about a battery, there's different systems, obviously. But let's say like if your cathode, your anode, your material starts to like agglomerate and lose surface area, become less effective over time, deactivate slightly. These things happen right over time. I would expect the double layer capacitance to also decrease because the surface area might be decreasing. Like if you have a high surface area with this like nanostructured particle or something like that, let's say, and then over time, you start having agglomeration, ripening of particles, growth of particles, your surface area starts to decrease as your materials start to become less effective over time. Probably that means that your double layer capacitance may start to decrease as well because it's proportionate to the surface area. And then as it changes as a function of state of charge, so it kind of depends. So like, for example, it's a bit, again, depends on the system you're studying, but like if for like a battery, you can look at it as like, in theory, when you're fully discharged, let's just say, I'll simplify this. I was going to make it a little more complicated. Let me put it this way. When you're fully discharged, the charge transfer resistance is quite high. It means that it's hard to get energy out of a system that has no energy to give. When your battery is fully charged, the charge transfer resistance should be low because it's really easy, relatively speaking, to get energy out of a battery that has a ton of energy to give, right? So that's sort of like charge transfer resistance. As far as the double layer capacitance, I'm not sure. Again, it probably depends on the system. I'm not sure that would change very much. And the solution resistance is probably not likely to be any different because that's just determined by the physical sorts of characteristics of your system, your cell, your leads, the electrolyte, unless the electrolyte is like dramatically changing, things like that, the ohmic IR drop, unless those are dramatically changing or your electrolyte's getting really ripped apart or something like that, those shouldn't change much at all. That's a function of the physical characterization and construction of your cell. So I hope that answers that question for you. We can kind of head back up.
Yeah.
We're going to, I apologize if you asked a question, you're still waiting. We've got a lot here. We're going to try to get to them as fast as we can from the beginning here.
Yeah. Well, I want to get this one from Abra Demika Ambaye. Which potentiostat is good from auto lab, biologic, and CH chem, and so on? I think we're going to say none because we work for a different company. We're a competitor to all of those.
Yeah. So we're Pine Research. We make our own potentiostats.
Yeah.
But no, I mean, we have many competitors.
Yeah.
They all make good stuff. You're not going to hear us badmouth our competitors. Biologic, Autolab, CH, Gamry, Princeton, PalmSense. Yeah. Now I'm just listing competitors. Yeah. If you have any of those potentiostats, they certainly are capable instruments and I mean, it depends on what they all are, their specifications are, but it just depends on what you're looking to do here. I'm not going to give you a breakdown of our competiters.
We also don't even know all of the specifications of what they do. Anyway,
we only really know our own company's equipment as far as that's concerned. I think Abera had a question previously, which we kind of already addressed, but it was just about, it was about on how to do impedance for liquid solutions. I mean, how you do impedance in a liquid solution is no different than how you do any electrochemistry system in any liquid solution. I mean, it's the same thing. And I just thought I'd mention briefly, right, that you set up your system with your reference working counter electrode, whatever, hook it up. And then I showed you our software previously, like get your impedance parameters and click go. There's nothing, in other words, there's nothing special about impedance necessarily as it relates to, running a test. You set it up and try to run. The only exception to that is you want to, with impedance, more so than a DC technique like cyclic voltammetry or chronoamperometry or something, you want to try and make sure you've minimized cell cable length and extra connections if at all possible, because those will more likely impact your impedance data than they are to impact your CV data. So if you have like your potentiostat lead connected to a wire, connected to another thing, connected to another thing, connected to your electrode, you're probably going to have a hard time getting good impedance data.
Yeah.
Okay. So what do we answer? The Bia had one up there. What do we?
Yeah.
Electrode.
Yeah.
I
You answered that one.
Yep.
We
did
did talk
this
about
CV.
chemical.
Yeah. Sorry, we're
Did
getting
the
here.
CV. Yeah, we're just catching up.
Yeah. Can water to form any possibly hazardous compounds? ChatGPT was warning about this, but as I understand it, sodium sulfate electrolyzes at a voltage above water. Good question. Sodium sulfate. I don't.
Correct.
Yeah, I don't.
Because there's no like
sodium sulfate is just a regular innocuous salt. Like what?
Yeah. So you have to go way above. Like if you're in water, you have to go way above the. And of course, it depends on the electrode material that you're using, but generally speaking, you're gonna electrolyze water way before you electrolyze any sodium sulfate.
But it's like sodium sulfate or potassium sulfate or potassium nitrate, like nitrates and sulfate, like SO4 2- and nitrate NO3-, right? Like these are like just innocuous salts that I'm not saying that you can't have some reaction that would happen with them, but like from an electrochemistry perspective, yeah, like they're stable in their state. Those are stable electrolyte, material, like salts, right? Like
well, yeah, but like if both they're gonna exist as ions in solution. And like if you're reducing sodium to solid sodium in water, then it can be explosive. And oxidizing sulfate to say like SO2, I don't know if you would find, you form like
we could look at the chart.
You could look at something like that. But these are like really high potentials, like either really, really negative potentials or really, really positive potentials. You're bubbling so much. You're bubbling so much water converted into hydrogen gas and oxygen.
You've got other problems.
Probably, you have all kinds of other stuff. Only if you're doing this in like metal, or not metal, in like oil, something that can actually, have a really big potential range. Could you do that kind of stuff?
I'm just looking at the standard potentials table and see it. I can see it, but
yeah, I'm gonna see if.
But anyway, I think be careful with ChatGPT in general. It's a great resource. I know I've used it at times to like analyze code, kind of give some tips about that. But it's as smart as whoever programmed it, right? And so it's probably more likely to give you some sort of general safety advisory. If you say like using sulfate, it might be more likely to just say something like, be careful, you shouldn't hurt yourself, don't play with chemicals. Like that may not be entirely accurate, I grant, but I'm not sure that I would if it might know have a database like the one I showed previously with the standard potentials. Like if you might ask it like, what's the potential at which copper reduces, it might be able to pull that up for you. But I'm not sure how reliable you want to be with it as it relates to specifics like this, right?
Yeah,
this is what the scientific literature is for, or stuff like that, right?
Or asking us.
Yeah, or asking us, which we clearly are smarter than ChatGPT. Okay, next question.
Let's see. I think
Raja says, how can we know the optimized potential window for CV? Do you want to talk about this again?
Yeah, I can talk about it.
Talked about this a couple times. Alex is good at this. One of the previous
I think it was
episode.
It was second or third. I talked about determining the potential window. It was one of the early ones. But determining the potential window or optimizing the potential window for CV, this is for any kind of situation. But really what you want to do is take your electrochemical system. Doesn't matter if it's aqueous or non-aqueous, or you're using carbon or copper, whatever it may be. And really you just want to make sure like these are kind of pseudo-sacrificial, and just sweep the potential as far back as you possibly can. And then you'll start to see these big increases or decreases on the edges of the voltammogram that are associated with either the working electrodes breaking apart or the counter electrode's breaking or the electrolyte is breaking or something is breaking, and then you have identified your potential window. It's like, oh, I can't sweep beyond this range, basically. And that range, it may or may not be bipolar and asymmetric. So asymmetric refers to, is it like plus minus 1 volt, plus minus 2 volts? Or is it something like minus 0.5 to plus 2? That's an asymmetric potential window. And then bipolar just means it can access negative and positive potential ranges. So just to kind of get through some of the questions quickly, you just have to try it experimentally is the best way to determine what the optimal potential range is, because each electrochemical system is different.
Yeah.
Yeah. That was helpful.
The next question I see from Sashin says how to check self-discharge and leakage current of a supercapacitor using a potentiostat. So things like this, you have two tools. One of them is OCP and the other is ZRA. So to check if your capacitor is self-discharging using a potentiostat, probably you just want to measure OCP for an extended period of time. And so presumably you have it in a charged state, you can just connect the two sides of your capacitor to your potentiostat and measure open circuit potential. And so this is in a situation where no current, at zero current, what is the potential? And so if the potential is dropping, it means it is self-discharging, right? I mean, presumably it's got some potential at charge state and some potential at discharge state, right? And so to check for a self-discharge, you should see if the voltage is stable over time. And what that time is, I don't know. I mean, it depends what you're trying to see. Does it self-discharge over an hour or over a week? You could take periodic OCP measurements and see how long it's holding its voltage or whatever. Yeah. As far as measuring the leakage current, this is tricky actually, because what I was going to do is suggest a ZRA measurement. ZRA stands for zero resistance ammeter. It's a fancy term for short your system and see how much current you get. Well, if you short your supercapacitor, it's going to immediately discharge. So and you'll measure the current from it, right? So, but that's different than leakage current. So what you're kind of asking is, if it is, let's say I'm measuring the open circuit potential over time and it's dropping, well, how much current is being leaked or causing that discharge? I mean, practically, I'm not sure how you'd measure. Like, you'd have to have something in some. I guess it's tricky. So one of two things is if you had it's almost like if you put a multimeter in line, like in series with it to measure any residual current or something like that. Because at OCP, the potentiostat's not going to measure current's zero. It's, that's the point of OCP. OCP measurement. And if you're trying to, if the leakage current, like if the, the mechanism for a leakage, I don't know 100%, like if it's happening sort of internally, you know what I mean? If there's some sort of like you'd call it like a soft short almost, like there's a pathway for electrons to short between anode and cathode or something, but not like a piece of metal between them. Sometimes you call that a soft short, and that can lead to some self-discharge. I don't know how you measure that because you can't get internal to your capacitor. Like you're not measuring really inside. So I don't 100% know how to measure the current, but for checking for self-discharge, the best I can suggest is really it's just a measuring of the open circuit voltage over whatever time frame you're trying to see if and how much it's self-discharging or losing its capacity over time.
Would it be possible to determine like a general measurement of the resistance or the impedance, and then you could tell as the OCP is decreasing, you can then use that ratio?
That's smart. I think
that might be one way.
Yeah, yeah. So that's a good suggestion. I don't know if it's perfect representation of it, because like when you're doing impedance, how many you have to make an assumption, which, like, if you just did like long-term test, let's say you're trying to measure the self-discharge over like 8 hours, just for some, example's sake, you every 10 minutes measure the open circuit potential and then take a quick impedance measurement, right? And then you can do Ohm's law or whatever to back out the current based on the potential. So there's that would be a way. I don't know that that is the leakage current.
Yeah.
Exactly. It's tricky.
Yeah, it's tricky.
But that is in theory a way for you to get the impedance, of your system. But again, what is the impedance? Is that just the ohmic drop? Is that the, over? I think that's a good idea and you're on the right path. Exactly what that impedance is and whether that current that you would back out of like V equals IR or Z equals IR, or V equals IZ, excuse me. That's a cool idea. I'm not 100% sure about it, but I wanted to show if you had one, there's
I'm trying to catch up. Like there's still a lot from the beginning.
That's what I'm getting to. There's one about a wave driver 100. If you answer one, I want to get somewhat
sure.
So Srijib asked if I want to check power density curve of a battery, how is it possible with a Pine wave driver 100? I can actually show you that.
Oh, okay.
While I get stuff ready,
I'm actually curious about that.
Yeah, why don't you answer something?
Let's see,
while I get some, I have an archive. I'll show you this, Srijib, if you're still.
Oh,
here.
okay. I can actually. Oh wait, no, I'm not.
Oh, yeah,
that's okay.
Here,
Give me.
You do that. I'll use. Oh wait, we can't both use it.
No, we can't. We can't.
We have one computer.
We have one computer, which is all we need. And I have another thing. So let me.
Yeah.
I'm using my phone to determine to also watch the chat.
Scroll Instagram. It's always Instagram for some reason.
So just give me a second. Race Band had another question. How can we calculate the diffusion resistance when it is represented by Warburg or constant phase element? So I think the impedance associated with diffusion is the Warburg itself. So but right. Just yeah, like what part? Because it's a huge tail, diffusion resistance. But oh yeah, but I guess that's like, yeah. So once you do impedance and you use a Warburg element, when you do a circuit fit to your EIS data, you will find the impedance associated with just that Warburg element. There'll be a value assigned to it if the fit is correct or pretty good. So hopefully, Race, that hopefully answers your question. Do the EIS data, get that long tail, do the circuit fit that has a Warburg element, and then when it fits, it'll calculate the impedance associated with that Warburg element, and that's your Warburg or diffusional resistance. So I'm scrolling back up. I'm trying to get some people in order.
Let me answer this one now. I just got the data ready.
Sure.
Got it. Sorry, I didn't mean to cut you.
No, I'm still reading.
So this was again a little bit ago, Srijib, if you're still here. I want to check if power density curve of a battery, how you get a power density curve. I'm going to try to show you this. So I don't have the potentiostat to here exactly to show you, but I do have the data from a Pine potentiostat. So for example, if you are getting a polarization curve or you want to get a power curve, basically, okay? So this is like LSV data, right? So current versus potential. So what I've done is I have my metal air battery, right? Here's OCP was up here. This is, you can see about almost a volt, 0.9 volts. Okay. And I just dropped the potential. I went this direction as my mouse is moving. Right. And I, extracted current out of it. And so I got whatever, 50 milliamps of current, 60 milliamps of current. So that's my LSV. So the first thing that people typically do is you want to get the polarization curve. And polarization curve is really just, I need to flip the axes, right? Typically we show voltage up here, current up here. So I just flip the axes. I get this. I can do it live. I already had the answer there, but so here in Aftermath, I'm going to do a transform in a basic math operation. I'm going to swap X, Y. I can replace the trace. and there's my plot there. Okay. I think I just negated the current here. So yeah, I had a sort of a plot pre-prepared. It doesn't really matter, positive or negative. This is just a convention here, right? So, so I have my, I'll switch to this one though, actually, because the positive is just a little bit easier to look at. So anyway, this is the same curve. This is just, I just made the current positive. So this is your polarization curve, right? So dropping the voltage, and I'm starting to draw current from my cell. So the power curve, right? Power, watts, is the equivalent of volts times amps. So I just need to multiply these two. And so what I can do is, again, apply a transform, basic math operations, and choose, what is it, XY product. And what I can do is not replace the original trace. I want to add it. And I'm going to get my power curve. You see, it's going to add, get the legend here, it's a little bit big. It adds the axis over here already because it knows it's a different unit, and it's power. And so I'll just make this line a little thicker. But this is how you get the power curve, right? This is the power milliwatts here, but it's just at all points. And so typically this kind of analysis for a battery, for a fuel cell, you're finding the point of your maximum power. And that's the, you know, for your application or whatever, that's your ideal or optimum operating, you know, current draw or whatever, right? So that means that, okay, well, at 30, whatever here, 40 milliamps of current draw, I have my maximum power, and that's a corresponding potential of it or whatever. Okay, so but it's as simple as multiplying my polarization curve x, y. That's how you get your power curve.
And I guess you just divide it by like the mass to get the density.
Yeah, exactly.
But yeah,
So I can do that. It'll
you
probably
can
be
actually-
weird. It'll add another
yeah,
axis.
it'll add
Yeah,
another
I'm running out of axis. Yeah, if one of these was whichever one I like current, usually you do current density. If this was per area or per mass, then the power would also be power density. So yeah, so you can do them on a specific basis or not. So there's that.
All right.
Is there
So
okay.
there's one from
next?
Nithan Chandra. What are the better input signal frequency range to capture the SEI layer resistance when we have EIS data at different cycling stages? So I guess he's talking about like what frequency.
Trying to find it. I found it. There it is.
Oh yeah.
Sorry. What are the better input signal frequency range? Capture the SEI layer when we have EIS data at different cycling stages. High frequency. So probably like
megahertz to
no, not megahertz.
Oh.
Probably like 50 kilohertz to 1 kilohertz. Probably.
Okay.
That's a guess, but typically the SEI shows up at higher frequencies, just at like you'll have like IR drop, uncompensated resist. It's not uncompensated, it's two electrode, but
yeah.
That's the wrong term. But anyway,
Sure.
The ohmic drop at the highest frequency intercept, and then, you know, inductive effects if you go really, really high. And then usually it's SEI, and then it's anode, and then it's cathode. So the SEI is usually at the higher frequencies. But if you go to too high frequencies, you're going to start getting inductive effects, and you don't really need those because they're often useless. So so my answer is that usually in the kilohertz range, probably higher frequencies, you're usually getting a lot of times you'll see a kind of small-ish semicircle or semicircle-like feature at the high frequencies that usually corresponds to the SEI. Okay, let's see. CV, we got to these. I keep going back too far to make sure we don't miss anything.
I think
optimized potential, we got that. Yeah, I'm just making sure we didn't miss
Yeah,
anybody. I'm trying to do
I think the next one is Sumital Patel.
Okay.
Why sometimes pre-electrolysis is going to do before going to electrochemical study. Is it impactful? If yes, how? So I think what he's referring to, sometimes you might see in a paper, like before any CV data has been measured, they'll actually hold the potential like at the starting point for some period of time before they actually do the experiment. And The reason why they do that, it can be impactful. It can be, not always, but it can be. And that is, if you think about when you put all of your, like your electrode is in air before it's in solution, all of them. And your solution, you just poured it into a cell. So it's all, it's kind of sloshing around, it hasn't settled. So all kinds of stuff is happening. Like I don't want to say it's traumatic, but like, it's kind of a traumatic experience for an electrode.
Yes.
To like go from being in air and like there's, it's this nice, like, you already got some stuff on, the surface, there's always kind of stuff on the surface in air. And then all of a sudden that stuff's getting like displaced. There's all this solution, electrical double layer is forming, all kinds of stuff. So people usually hold the electrode at a quote pre-electrolysis point before doing an experiment to allow the system to equilibrate. That's really the idea.
So just as a visualization of what you just said, you can kind of think of it this way. If this is current up here, and this is like time equals 0, right? If I'm going to start my process right here, whatever it is, cyclic voltammetry, chronoamperometry, whatever, and I start by applying whatever potential, and then I'm going to measure my current, if I'm doing CV, my CV looks really bad, whatever it is, at time 0, and you shouldn't go backwards in time. So I shouldn't have, this only goes this direction.
This only goes that direction.
The point is that once I start applying potential, what you really have is this decay, right? So this decay that happens when I start applying, this could be like a millisecond or a microsecond. So it might not matter at all. But it could be a second. It could be 3 seconds, right? If you have a very slow process or something like that, or a very large electrode surface area where there's a huge amount of double layer capacitance that takes a bit of time to set up or something like that. In which case, you don't want the beginning of your actual experiment to be impacted by this settling nonsense. You want that to be out of the way. So that's sometimes why people will apply this 1 to 3, 2 second, settle pre-electrolysis thing. In our software, sometimes we call it like an induction period, right? And then you start doing your CV or whatever. This is like the worst drawing of all time. So my point is that you want to let that sort of traumatic settling, whether it's
very traumatic,
whatever,
you
want to try to let that process kind of be done with before you doing the real thing that you care about. Right. That makes sense.
I hope that makes sense.
Yeah. Sapanta says for an electrolyzer in terms of impedance and using aftermath for analyzing circuit fitting, I could not find available circuits. And you have a quarter circle and a half circular. Yeah. So Sapanta, can you suggest any model? I did the thing you explain in EIS circuit fitting PEM, but it doesn't work. I'll tell you the same thing that we said to someone. Pavel earlier asked that, was having a look at EIS and not quite sure how to analyze it or fit it. It's hard to answer this question, when I can't see your data right now, right? The good thing about this live stream is that we can show visualize things for you, draw them in our terrible artistic ability. Well, at least mine anyway. And but you can't show us. Right. So here, our email. I'm trying to reach the keyboard.
Yeah, go for it.
So here, I'll put our email. You can send me an email if you want to have a, I don't know, offline kind of a thing, or you can probably send some data or photos. We might be able to help you there. The other thing is, again, as I said, I'll just sort of repeat it, is that I can try to give some quick general advice if I can, obviously in this format. But if you're going to send some data, I can try to give quick opinion, and if it's something that would be a longer form, kind of like take some more time, if you wanted to have like a one-on-one, video discussion, so sort of a consultation. If it dips into the realm of consultation, we can offer that, service for you. But that would be a discussion for later, right?
Yeah.
It's just, it depends on exactly how much help you need and to what degree, you know, you need it, I suppose, or what frequency you need help, you know, or some discussion. We can do those kinds of things. But we would have to kind of check offline, you know, without seeing your data. The best I can tell you is you can try a number of different Randall's elements, like just add some more Randall's elements. It's not something I usually suggest because it doesn't necessarily mean anything, right? You run into that, like, well, what do all these Randall's elements mean? But sometimes just by adding more of them, you'll start to fit some of these features, and then you can maybe try to back out later, like what they all mean, if anything. And then it's, you know, if you tried I don't know, I think in that electrolyzer one, I don't remember, I think I did a Warburg short or something like that, maybe. The other thing I'll say is that, you know, you'd have to, again, this would be something we could check out later or through email or when a more in-depth conversation. But when you say it doesn't fit, you know, there's a difference between doesn't fit at all and it doesn't fit like really as well as I want, but maybe it fits okay enough to the extent that I can still say, well, this is the best fit. There's some non-idealities. Check Kramer's Chronic to see how valid the impedance is to begin with. You know, maybe it doesn't fit as well as I'd like, but it fits well enough that it's as accurate as I'm going to get, and I'm going to use this analysis anyway. Like, don't get hung up all the time when you do impedance on hoping that the line looks like the dots, like perfectly. It's almost never going to happen with real data, really perfectly, right? Sometimes you have to settle for a pretty good fit. And that can sometimes be okay. And you can publish data with fits that don't line up like absolutely perfectly. You can absolutely publish data like that too. I have, you know, I've seen a lot of it. So it's not like required that it has to, like, you know, fit lockstep with your data 100% of the time. There's one for Spectra. This is for sure.
I think it's Dooley's.
Yeah.
Dooley's. You're asking, is spectroelectrochemistry the same as chronoamperometry, but with an added UV-vis plot? Thanks. So yes and no. I'm going to share screen. It depends. Sort of say there are many different kinds of spectroelectrochemistry experiments, but basically the idea behind any spectroelectrochemistry experiment is that you have both electrochemistry data and UV-vis data like combined together. So commonly, like when we do spectroelectrochemistry with our software, what we'll do is we'll have kind of a potential versus time. And what we'll do is we'll hold the potential, and then at a specific time, we will step it. So yes, just like a chronoamperometry experiment, hold it, step, hold it, step, hold it. And then at each of these points, and I'll use a little star to kind of mark like where it happens. But basically at each one of these little stars, you're getting a spectrum, or you're collecting a spectrum. So you'll get some kind of wavelength. Hold on. I'm gonna use the typing tool, because so you're gonna have like wavelength, which is usually in nanometers, and then you're gonna have something like absorbance or transmittance. So absorbance. Usually on the other side, and then you're gonna have like your spectrum, and each spectrum is going to be, you know, like associated with a particular potential that's like applied, and maybe you're looking at some unique, you know, some unique feature or something like that. You know, I'm making up some of these things, but like this will be at like you know, 1 volt or 1.5 or 2 or whatever, they each correspond to the step. So that is how we do spectroelectrochemistry. There's also spectroelectrochemistry that we don't currently offer, but I want to have offered, where you take multiple spectra with a step. So that would be the case of having like a couple of these stars while you step the potential. So Yep, spectroelectrochemistry is that. It's just a combination of timed potential electrolysis with a UV-vis spectrum. Hopefully that was helpful.
I'm glad Alex answered. I'm not a spectroscopist. So I just, the next questions from, I see here about Gonzalo had said, you just had your first event for like scientific stuff, and you were asked what happens at the 3 electrodes in CV from a colleague who never used CV. Felt great to properly explain that in public, isn't it?
Nice.
Good job. Yeah, I'm glad you're able to drop some knowledge on these people. So congratulations. I guess.
Congratulations.
Yeah. I'm glad.
Feels good.
Yeah, it does. I'm glad to hear that. I like hearing about your science wins.
Yes.
You know what I mean? Okay, so Haider Ali says, when our main target and an anode material is to see capacity and stability, we see it from galvanic charge discharge. Okay. And then we need EIS and CV. So the purpose of CV. Yeah, so CV isn't used as much in those systems, because CV is usually used to find, well, it's used for a lot of things, but I mean, you know, I always find this harder to explain than I think it should be.
Well, why to use CV?
Like why you don't use CV. Batteries, when you do cyclic voltammetry in a battery, you don't usually, like, you have to scan really slowly, because it's like doing cyclic, like, okay, so if you think of CV at like what's a normal scan rate, like 50 millivolts a second to 100 millivolts a second, right? A battery will have a range of a volt or something, right? Like between charge and discharge, like a range of like 1 volt, just give or take. So just thinking about this roughly, if you scan at 100 millivolts per second over a volt, it takes 10 seconds, right? Did I do that math right? Yeah. Like 100 millivolts per second.
Yeah.
Over 10 seconds will span a volt. That's the equivalent of charging a battery in 10 seconds. Really fast, right? So like CV isn't the appropriate, you don't want to modulate the potential that quickly. You're changing the condition of your battery way too quickly. It's not meant, you know, it's a storage. The capacity of a battery is way higher than the capacity of most other systems, because it's storing charge. It's a high capacitance. It has a, you know, that's its purpose. And then, you know, CV can be used to clarify the position of a redox process or a peak or something like that. That's just of less concern with a battery. You know, like with a battery, you are doing that galvanic charge discharge kind of process, right? You're trying to see how much current can you pump into it or take out of it for how long. That's what a battery's for, right? You're trying to get current out of it to run your thing, power your device for however long, for whatever period of time. So CV does, I mean, it's not that people don't do CV. It's just that it's not the primary kind of thing that is used in the analysis. Now, EIS is, and because one of the things that EIS, for example, can get you are those capacitances. You know, batteries in particular, or our supercapacitor, all these kinds of systems, you know, usually have very large capacitances and low resistances. Okay. And so impedance is a way to measure resistance and capacitance. So you can directly get a measure. And I talked earlier about like the SEI and the anode and the cathode. You can get impedance, resistance of all of these processes by doing EIS. And so that's what EIS really gets for you in those systems. Session has a question. Did we answer this one yet?
Session, which one?
I think not.
I don't.
What is the typical arrangement of cations and anions during electrochemical activities? Well, solvated is what they are. They're solvated, which means they're surrounded by water molecules.
Yeah.
An arrangement, you know, that it depends on what you're doing.
Maybe it'll be different at the electrode surface.
Yeah. Let me pull up. Wait, did you do the knowledge base article? Didn't you do, you did a cool.
That has like a picture.
Yeah. It's better than the one I did in my slide. You showed Didn't you do?
I
Is
mean,
that in the which one's that in? Yeah, with the what is it? The double air capacitance thing?
yeah.
Did you
It's in the CV. I know it's in the CV video.
oh, maybe it's just the CVV. That's what I'm thinking of.
So yeah, so
I'll
if you
pull up
go
that
to,
PowerPoint slide. Well, we can.
yeah, oh yeah, either one's fine.
Yeah,
Go
I
for
thought
it.
maybe in the knowledge base article you had the double layer thing.
Oh, maybe in the EIS.
Oh, is it in the EIS
Maybe
one?
it's in the EIS.
Let's find it.
Give us a second.
Yeah.
Also, let us know if this is what your question is,
Yeah.
Sachin, about the arrangement of cations and anions, just to make sure. And
Yeah.
also just kind of double checking what people are saying and asking. I think we're getting through most of the questions. Let's see.
See if I can pull this up here.
Yeah, we're just looking to see if basics, the
Basics,
top
that's the
one.
one. Okay, let's see if this you made a good cartoon for this.
So maybe
It's in this one. Is it? Yeah,
there
it
we
is.
go. Okay.
Yeah,
I think that's
that's
okay.
This is an answer.
And
it's part of an answer. So what's happening to anions and cations? Well, when you're in a 3-electrode system, you have positive cations and negatively charged anions, right? And the way Alex has drawn this is that part of the arrangement or the physical orientation of them is that, generally speaking, negatively charged species are larger. That's a
general chemistry.
Yeah,
like anions are
what's
larger than cations.
Yeah. Well, it's
the
because
atomic radii.
It's because it has more of a negative, just more negative than positive, and so the electron cloud grows. Whereas with a cation, it loses an electron. Now the nucleus is more intensely pulling on all of the electrons, and they're closer in, so it's a smaller radius. That's molecular orbital theory, or the Bohr model. Whatever the right
electron negativity. The atomic radii. I don't know whose model.
Yeah, whatever it is. But the point is that is that so in some sense there's the size of the ions, and then the solvation is just that water molecule. Generally, anions and cations don't exist like by themselves in solution. They're solvated. They're basically surrounded by a matrix of water molecules. Yeah. And so you'll have hot water arranging itself. You have, for the anion, the positively charged hydrogens will be more closer to the outside, whereas the negatively charged oxygen species for the cation, they'll move depending on the charge and how you polarize your electrode. So if your electrode is positively charged, then negatively charged anions will be drawn more towards the surface. This is where your double layer capacitance comes from. Yeah. They migrate through solution. That's how you complete the circuit and the system, essentially, is through the movement of these ions. It's like ferrying charge. That's how charge, the other part of it is in your potentiostat, or whatever wire connects your two electrodes. The other part of the charge balance is through these anions and cations. So, if a negative charge moves from left to right, it's the same as a positive charge moving from right to left, or whatever. And so they're balancing charge. Yeah.
There is one, I only learned this a little bit later. One subtle correction that I didn't make is some of the negatively charged anions are actually in contact with the electrode surface. In this picture, I don't have it, but it's not just that there's a solvent molecule at the electrode interface.
Just
some of the anions are physically touching the the thing. So so you can I guess if you want to annotate, you could erase.
So this is
molecules
not here. Well, not always.
Yeah. Not always there.
That to me is such a nitpicky thing. Like, okay, I know. This is just this is a really useful cartoon. And the fact that you just happen to draw the anions with this solvated ring doesn't necessarily mean that this surface, of your anion can't actually touch here. It's just, this is just a good illustration. But hey, people are gonna nitpick's gonna nitpick.
There's been some nitpicking.
Just defending your cartoon. It's good.
Thank you. There's another thing. This was I talked to one of our colleagues who's way smarter than both of us, Lee. And
that's true.
And Lee said another thing is, depending on the charge of the electrode, will also, like, if you have an anion that's like connected to a positively charged surface, it actually, if you reverse polarity, it's actually kind of hard for that negatively charged anion to come off. There's just, especially with conductive metals, in a way, conductive electrodes, they have a lot of, conductive materials have a lot of negative charge naturally, right? But without applying the potential, they just so happen to have it. So there are certain orientations of anions and cations near the electrode surface that are on the electrode surface that are kind of strange. Just letting you know that. Hopefully this answers your question.
Yeah.
All right.
Okay, let's see. Raja,
Yep.
I'm not sure if I answered that. During battery charging, anode is reducing, but I think battery is oxidizing at the anode. No, during charging, during, let me think
So
through and make sure I'm getting this
during
right.
battery charge, anode is reducing, but I think battery is oxidizing at the
No,
anode.
it's so
Because
the charging process of a battery. So,
and this may also go into Hiral Kumar's question: is cathode always negative? Because I think we're talking about just
okay, so
the difference between.
First of all, yeah, if you're talking when you're talking about the cathode being negative, that's a semantic thing. We call the cathode the negative electrode, and the anode the positive electrode. So like on a battery, right? If you're looking at a battery, or whatever, like a commercial AA, AAA battery, usually you. Actually, I said it backwards. The positive is the cathode, and the negative is the anode. So, your battery will have a plus on it and a negative on it, right? The one that's labeled plus is the cathode, and the one that's labeled negative is the anode. Don't get hung up on whether the electrode itself is actually positive or negative. This is a bit of a semantic game. It's just a game of words.
Yeah.
Nothing is negative or positive on its own. Something is negative or positive with respect to something else, right? Like you're talking about potential. There's no such thing as like an absolute potential. It's a relative quantity. That being said, we just use the plus symbol to represent cathode for whatever reason, we just do, and the negative to indicate anode. Now to the question of charging and discharging, for example, if this is my research. Okay, so I did lithium plus as the cathode. Okay, and I did like a nickel oxide as my anode. You know what? I'm not going to use nickel oxide. I'm going to use the more common.
Graphite.
Graphite. Let me use graphite. That's what's most common.
You want to type
All right.
No,
the graphite reaction is Li plus 6C goes to LiC6. Okay, and then that's the cathode process. Okay, when a battery exists in a discharged state, there's no lithium in the anode. All the lithium is in the cathode. So your cathode might be Li, cobalt oxide. Okay, one of the first most common ones. Okay, to charge the battery, lithium goes from the cathode into the anode. That's when you're charging your battery. And so the lithium ions have to, this isn't the right reaction to it. I'm missing electrons here. So forget about that. But lithium has to go from the cathode to the anode during charging. Okay. So the reaction at the anode when you're charging up your battery is you're loading up this carbon with lithium ions. And so you're doing a reduction reaction. Okay. So that's what's happening during charging. And then during discharge, the opposite is happening. During discharge, you are getting the lithium ions to leave plus electrons LiC6 goes this direction, right? So the lithium leaves and it's oxidized. It loses an electron and it goes back into the cathode. So that is the fairly certain, that's the correct designation for which one is charging, which one's discharging, and which process is occurring.
Mhm.
Okay.
Yeah, hopefully that.
Yeah. In a sodium ion battery, if the electrolyte has sodium salt, did we already answer this? I thought we had the electrolyte has sodium salt and it dissociate into ions. And did these ions go into the anode to store in it? So, I mean,
I don't think we answered this because we are talking about like sodium
Yeah.
sulfate and whether it was like
yeah,
you
this is a
electrolyze that.
different, this
This
is a
is
different.
slightly different from BIA.
So what I just described is a partial answer to your question, whether it's lithium or it's sodium. You load up your electrolyte with the ion of interest, sodium or lithium, because yes, those ions are going back and forth between anode and cathode during the charge and discharge process. So without an electrolyte between the anode and the cathode that is full of the ion of interest, you have to wait for a single sodium ion to diffuse its way all the way from the anode to the cathode, or vice versa, whether you're charging or discharging. That would take a long time. So you have electrolyte with strong concentration of like LiPF6 or sodium, whatever the salt they would use for sodium ion batteries. I'm not 100% sure. I didn't work with those, but you have those ions in solution. And so those ions are, I mean, whether that exact ion itself is going in and out, I mean, that's probably not the case. It's not like one ion is running back and forth, but you have a massive amount of lithium or sodium ions to help the charge and discharge processes occur back and forth between the two electrodes.
Okay.
I see there was the CV discussion with
had the
Five.
CV
I think we're all
discussion.
set with
I think
that.
we're all set with that.
Seven
me.
Yeah, what's the question?
Why CV mode is used for activation process of electrolysis cell station? So I think what this question is, me, and let me know if I'm correct or incorrect. Sometimes people will use, they need to quote activate the electrode. And activate is, I think, somewhat of a loaded term. But for example, carbon sometimes needs to be quote activated. And what that means is, again, when you have something like a carbon electrode in air, and then you put it into a solution, it has a traumatic experience because all of your, the carbon electrode has stuff on the surface. There's tons of like volatile organics that are just in the air. As humans, we emit sulfur and all kinds of stuff, and that gets onto surfaces such as a carbon electrode. So in your carbon electrode in solution has all this stuff on it, like attached to the surface. So some people will use cyclic voltammetry to just sweep the potential back and forth to get rid of some of those things and kind of prepare the electrode to do an experiment. An actual CV experiment where you're studying something. Because literally, you might get different results, like a lower current if you didn't activate the electrode, allowing all of its quote active sites to be accessible. So that's like one, if I'm getting your question correct, that is why people quote activate an electrode, is because there's just stuff on the surface and they need to get rid of it. Hopefully that's helpful.
I think that is a good answer. Heider's another question that says, in a lithium ion battery, why do we use lithium salt for the electrolyte and not some other salt? Well, so, I mean, I think I did just answer that. The reason is that you're passing the lithium back and forth between the anode and the cathode. That's the charging discharging process. And so to illustrate that again, if I can here, if you think about the process of charging and discharging, right? When you are, I keep drawing them in like opposite sides. I had anode over here last time, so now it's just getting more and more confusing. My anode over here and my cathode over here. And so when I'm charging, lithium is leaving my cathode and going into my anode. And when I'm discharging, lithium ions are basically leaving my anode and going into my cathode. Okay, well, that is it. Like, however much distance, this might only be a few millimeters or something, but this lithium ion is small. So if I have a bunch of lithium ions in solution, then it's kind of like there's a big train of lithium ions. And so when this one starts to move, it just pushes each of them ever so slightly. There's already one right here. So I don't have to wait for this single lithium ion to just diffuse. And then 10 years later, when it finally makes its way over here, I got my charged battery. You know, it's like that's, you saturate your solution with ions to help that work, help the charge transfer, you know, quickly, right? In the above CV, you say an oxidation electrolytes donate electrons, but an actual electrons come. I'm not sure if I said that I'm not sure if that was what.
Let's see.
This might just be
oxidation.
This might just be a communication mismatch here or something. Oxidation is where an electron is lost from the electrode, not the electrolyte.
Yeah.
Right. An oxidation process is when an electron, you know, at the electrode surface. So, okay. So the oxidation during discharge of a battery is like, again, this process, Li, you know, C6 loses an electron, a lithium ion is released, and, you know, you're left with carbon, 6 carbon, whatever. So something like that. So anyway, the electron is what's leaving here. You're losing an electron. It's on the electron is in the right hand side of the equation, right? This is like sort of like, you know, fundamental electrochemistry. In actual electrons come from cathode. Yeah. So I mean, that is the other part of that, right? When the electron leaves, well, it has to go somewhere. So it goes to the other one. It goes to the cathode. That's right. When you show it leaving, it's not going into, you know, the way I've drawn this E minus is in the middle of my diagram. I don't mean that it's going into the electrolyte. The electron is going through the external circuit to the cathode. So if that's what you're talking about, the electron comes from or goes to the other. That's correct. That's where the current, that's where the current is passing. So that's just somewhat of a logistical thing, right? The current of the electrons are going to the anode or cathode or whatever, and they're not going. Electrons aren't just zapping through the electrolyte between anode, cathode, or working counter electrode, whatever you have. That they go.
Right. Yeah. We have now. I'm wondering if you want to. We have a few questions from some members. Race, Bannon, and then Ramachandra, as well as Kempor towards the end have some questions. Oh, so Ramachandra had a question about, does chi-squared of circuit fit define the robustness of a system? I would say that's probably no. It's just whether or not just how well your fit is.
Yeah. I mean, I don't even know what robustness means. I think, is it Gamry? One of our competitors they use like the wording like goodness of fit, or they use something like that, like, you know, wording like that. As far as I am aware, it's basically just chi-squared, and they call it a different terminology. And so this goodness of fit, robustness of, you said system fit, like, you know, robustness of system, like what does that mean? Yeah. And I'm not necessarily asking you for an answer. I'm just saying, like, that's a bit vague, right? Chi-squared is just an indication of how well the circuit fits the experimental data. That's it. That's all it is. So we would have to have a better definition of what robustness of system means. That's a bit esoteric of a term, I guess. Strictly speaking, chi-squared is just a measure of how much the circuit fit matches your system. That's it.
Yeah.
So we're going to Race
Bannon.
Bannon has this other question. In addition to my previous question, if the alpha value of a constant phase element is 0.3, should we calculate the capacitance or take it as resistance? That's a good question.
Really good question.
Your alpha is getting under 0.5. I always try to answer these questions.
More resistant.
It's more
acts more like a resistor.
It's if you want to think about it, it's something between a diffusional element and resistance. Now, what does that actually look like? What does that mean? That's hard to tell, right? Usually this comes in the form of alpha between 0.5 and 1, right? It's like kind of capacitive, kind of diffusion. I always find it a little easier to think about that upper portion of alpha, because like an ion that's some distance from an electrode is a capacitor. But if it's moving, it's diffusion. But that's just like a capacitor that has a varying distance between the plates. So it's like, is it diffusion? Is it capacitance? Well, it's kind of both. Okay. Well, I can kind of visually work.
Yeah. You can think
but what's a resistor diffusion?
Or
physically, like what's it? You know what I mean? It's I think it's hard. I think the answer is hard. That's a really good question. And I think my best answer to you is I don't know. But you're thinking the right way is what I would say. You're thinking about this properly. Like it's kind of approaching resistive behavior. If you have this, or at the very least, it's like a really, really non-ideal capacitive kind of thing. Like it's a very heterogeneous surface, or it's really like non-ideal diffusion. Like there's something going on here. Once you start getting below 0.5, your constant phase elements, like in my opinion, the interpretation becomes really, really really fraught. Like it's hard to come up with like what exactly is going on here, right? It's like something very non-ideal is happening. But I don't think you take it as resistance. Like it's not equivalent to a resistor, but you're thinking along the right way. If I can say, I don't know how much better to say it than that, but I think that your thought process is intelligent.
Let's see. It looks like Ramachandra. Does the surface area, the working electrode, has an effect on capacitance in EIS?
Yeah.
Yes,
for sure.
So the bigger the surface area, the more capacitance. Generally able to hold more charge.
Yeah, exactly. Generally speaking, it's similar to, the higher surface area. You should have higher current, right?
Yeah.
Like if you do cyclic voltammetry, and you'll have more capacitance. Generally speaking, that's correct. What's a good what's a good, easily found, readily available material to use as a diaphragm or a membrane for a divided cell? So it depends on what the electrolyte you're using is. People use Nafion for proton exchange or acid solutions. Nafion is really readily available. It's I think it's made by DuPont, right? I think DuPont owns the patent on Nafion, right? But it's Nafion's used in basically all PEM fuel cells, right? It's still the state of the art as far as I'm aware. There are a lot of work. Shout out to John Varco at the University of Surrey, for years, I believe, has worked on alkaline membrane and alkaline ionomers for like alkaline exchange membrane fuel cells. So there are people working on that. I don't know if it's like a commercialized solution yet, but if you're doing alkaline kinds of things, it's not as far as I'm aware, like ubiquitous or convenient, perhaps. But apart from that, I mean, you can use things like thin plastics, like polypropylene, polyethylene, have some level of porosity. I think that can work. Just simple plastics like that can sometimes do, but it's tricky because it depends. Is it aqueous? Is it non-aqueous? You're weighing out the hydrophilicity, right? You don't want to have a membrane that lets everything through too quickly. Otherwise, you might as well just have one solution, and the thickness matters and stuff like that. But hopefully that's a decent, I don't know, overview of, you know, some of the options for a few different, you know, types of electrolyte.
Yeah.
So Ramachandra has another question.
Is there any way that can help us determine the number of molecules that are absorbed on the electrode surface by EIS?
I doubt it.
Yeah.
That's really specific, like the number of molecules.
Yeah. So I don't know about EIS. There are some DC voltammetry techniques that you can use to at least get a good grasp of molecules that are absorbed on the electrode surface. One technique is double potential step coulometry or chronoamperometry. So if I can, I can drive quickly. So coulometry and chronoamperometry are kind of, they're similar. But the idea, very simply, for this kind of experiment, and you may need to look up some of the equations that are in Barden-Faulkner, but the idea is you'll get this is something I used to do, but basically, if you apply a double potential step, so you get this, this is charge, and this is time. And then you would get this curve that looks like this. And then when you switch the potential, it would get this drop. And then you would get this curve that comes down like that. And basically the idea is you would collect the chart. There's an equation, which I don't have or know off the top of my head. But the idea is you apply a potential such that stuff gets absorbed onto the electrode surface. And then you almost do like a stripping voltammetry experiment, removing it from the surface. And when you kind of take the difference, if you call this like, I'm just going to say this is like a shaded area. Basically, it's just like, you know, it's like C1 minus C2, just like the charge from these two different areas. Any effect of the electrical double layer is removed because ideally you're making an estimate that the double layer charging isn't changing.
Yeah.
And all of the molecules that are oxidized from diffusion are gone, which usually leaves the difference. You'll get some difference, and they used this, I think it was like this symbol. This is like a gamma. I think it's capital gamma. I forgot what
it's either capital gamma or capital lambda.
Capital gamma, capital lambda.
Back to grad school.
And it is like absorbed. It's basically adsorption, right? So the idea is, okay, like you oxidize something, there's diffusion and double layer charging that makes up the current. And then when you strip it away, you take away the time dependent stuff, right? Like any adsorbed molecules their current is time independent. And when you take that difference, you're going to get this little sliver that is associated with the adsorbed molecules, and it's charged. So that you can then use Faraday's law and convert coulombs to molecules, and then you can to moles. Sorry, coulombs to moles, and then use Avogadro's number to convert that to number of molecules. I worked in a lab that basically did some of this kind of stuff where they were actually trying to measure number of molecules on a surface. And generally speaking, just to give you an idea, I think it's like for a reasonably mid-sized molecule, you'll get like 10 to the 13 molecules per square centimeter. That's the number for a monolayer. So that is that's a way you can determine, Ramachandra, the number of molecules adsorbed on an electrode surface. Hope that was helpful. And then I think so those are all those are the member questions.
Yeah, well, we can get back.
Going back.
I'll go back to. So AJ had a question. I think that was next. That says, why can aluminum 3+ it can't be reduced by hydrogen at very high temperatures?
Yeah, maybe it's a catalyst thing.
Maybe I don't know if it's but
yeah.
This
see if I can find that question.
The only hunch, and I don't know if this is in the right sort of ballpark. Is this it's like a metal hydride thing? If that's what this is, I don't know if it has to do with enthalpy. Like all that kind of comes to mind for me is like metal hydrides. Like, is it because it might be I'm not sure if it's like an endothermic kind of a thing in which like, most, I was just trying to find a quick thing. It's probably, the answers are probably more than I could search for very quickly. So I can't give you a very good answer, to be honest. But I think it has something to do with the thermodynamics. So either there's an answer that's totally outside of this, okay, which is certainly possible, or it has something to do with, how effective is the catalyst or whatever that you're using, okay. Otherwise, it might have something to do with the enthalpy. So most reactions of, what's the rule of thumb? It's like every 10 degrees or something, it doubles the reation rate. So something like that, right? Like, generally speaking, when you increase the temperature, the reaction rate increases, goes up. But there are exceptions to that. There are some reactions for which you increase the temperature and the kinetics decreases.
Yeah.
And is that's related? It's either related to the enthalpy or the Gibbs free energy. Gosh, yeah. Some of this is taking me back to like my early grad school, late undergrad days of thermodynamics and kinetics, and exactly what those appropriate relationships are. But for example, I worked with some metal hydrides once or twice, like very briefly when I was in graduate school, and they were always cold. Something about the metal hydride, I think it's like an endothermic process. It doesn't prefer high temperature. It might have something to do with that. That's the best that I can offer, is I think it has something to do with that. And I'm not much more sure, but it might have to do with it's a reaction for which the relationship is reversed, that lower temperatures are preferred kinetically or something like that. But again, that's kind of the best that I can give you for that.
I'm sorry.
So some of these, I mean, honestly, if they're a little specific, we don't always really.
Aluminum 3+ is very stable. It might also just require a higher potential. Like you may be able to get some crazy organic or inorganic reducing agents that have a much more negative reducing potential than hydrogen to actually reduce aluminum, but that's also another gas.
Is a quick one here. Larabe says, why is there a large difference between the first and second cycle discharge capacity in lithium-ion batteries? Because the SEI is formed. That's why. I've talked about this. Was it last week or the week before? I can't remember. But anyway, I know if you weren't here, then that is irrelevant to you. This question comes up from time to time. I think it's a good question, and it's generally speaking, the answer is the solid electrolyte interface. So, when you construct a battery, you have your anode and your cathode and electrolyte in between. Fundamentally, what happens is that the electrolyte actually decomposes to form this film on the anode primarily. And it forms a film that is of various decomposition products of the electrolyte. It's called the solid electrolyte interface or interphase, SEI. And that basically takes energy to do something like that. And so what it does is it can fool you when you do you construct your battery first and you do your first charge discharge. It'll fool you if you aren't aware of it into thinking that you have more capacity than you do, but that isn't repeated. Like that SEI, which is actually like a decomposition of various materials and organics and electrolyte products, prevents further decomposition of the electrolyte, as weird as that is. And so that SEI is necessary to facilitate further discharge and charge of the battery. And so actually what happens is when battery manufacturers make their batteries, they charge or discharge them like a few times in the factory before they load them into the car, phone, laptop, whatever, so that the expected charge discharge is stable by that point. Because if you assume the first charge discharge is how much it should give you, you'll be constantly at a state of like whatever 80% or 70% or something effective from there on out. because it's just the SEI forming. Okay, let's see.
All right.
Move down this one, I think. Challenge was
Screen printed electrodes.
yeah. So Abera has this question.
So yeah, Abera has the question. I have a challenge with screen printed electrodes. When I compared the modified screen printed electrode, the bare screen printed electrode showed me better electrochemical performance. Do we have any tips on screen printed electrodes? It's like, well, I guess whatever was on the bare screen printed electrode was awesome, and you covered it up by modifying it.
I mean, this is so specific to your application, right? So like maybe what you thought you modified it with that was supposed to help took away active sites or took away conductivity or was hydrophobic in an aqueous solution and actually repelled water or
increase the resistance.
Yeah, increase the resistance. So that made the performance drop. Like there's any of a number of different possibilities here, but this is one of the things generally, I would say tips or something about screen printed electrodes is that they're good for this kind of screening. You know, you might just be getting yourself an answer, which is that my modified process / film or material is terrible, you know, that's an answer. You know, maybe it's right. Maybe you need to modify your process or maybe, you know, maybe there's something wrong with the screen printed electrode, but assuming the screen printed electrode, the carbon is fine and whatever, it might just, you know, a negative answer is still an answer. Right. This is science. So that might be, I don't know, that might be your answer, I guess.
So it looks like Sapanta sent some data. I think maybe another week we'll actually have some time to take a look at it. Sometimes
we'll take a look at it certainly when we can.
Hopefully it didn't get caught in the spam filter, but thank you for at least letting us know that you sent it. All right, moving on. So
BS says in sodium ion battery.
We did talk about.
Oh yeah, we already
spoke about that.
Yep. We've got to the
Barry
Pemberton says.
Welcome back.
Yeah, we've seen your name.
Yeah, we've seen you before. When using a pseudo reference electrode like a silver wire, are there other good internal standards to use other than ferrocene, especially when looking at redox potentials at or around ferrocene?
Yeah, that stinks if you're looking at it.
Yeah, I don't actually know. I mean, so it's going to depend on your system. I'm assuming it's a non-aqueous system.
Doesn't Ruhex work in non-aqueous?
I have no idea.
I think it does. I think ruthenium hexamine will dissolve in both aqueous and non-aqueous. I might be wrong. I know it's a good aqueous one. But to the best of my memory, I think ruthenium hexamine. So that might be an option. I don't know if its potential is dramatically different than ferrocene. That's just the first one that comes to mind because that's like a really well-behaved system, you know, couple that could work. I don't have the most experience with non-aqueous. I've gained most of my experience with non-aqueous working here. You know, not from my own, other than lithium ion, but I don't count that. Like what you're talking about, like internal standards and stuff like that. Like, I didn't do much of that in graduate school, so I don't have enough experience with that. That's a really good question.
Like, ferrocene is also really, really like commonly used and cited. So that it's like, if you read the literature, people will use ferrocene, but that doesn't mean you don't have to use it. One thing, one idea, I have an idea for you. So I don't know how most people, when they do an internal standard, they just add ferrocene into their electrochemical test solution, and then they have the silver wire. What you could do instead is add ferrocene inside the reference electrode. So it's still like a fritted tube with a silver wire, or even another material, sort of say, like graphite even is fine. Something where, you know, like reference electrodes just have to have a stable potential that is with fast electron transfer, which ferrocene has. And this way, when you add ferrocene to the solution, that in a way pegs the potential of that whatever item. Like, you're using a silver wire, but you could use like graphite in the tube with ferrocene at a known concentration. And that would also be a way of you referencing ferrocene. You'd have to do a little bit of math to figure out exactly what that potential is. That's another way. Yeah. So you could make a reference electrode out of anything, but, you know, I've worked with some like cobalt complexes that have pretty good redox chemistry. They're all air sensitive though. So, you know, Gillian Dempsey has this like cobalt-oxime molecule. It's used as a catalyst, but it has pretty good redox chemistry. If you have ferrocene and then you have this other well-established redox process and you know the potential difference, you can just now, it's like, all right, it's stable enough. I know what it is, so I'm now going to reference it as my internal standard with respect to my unknown that is near the ferrocene redox potential. So those are a few ideas.
That's a really good idea. And I think the only, you just have to, you know, with non-aqueous systems in particular, it depends on the frit.
Yeah.
Right? So like one of the things that my company, our company is I've been working on, and anyway, it's done. We're releasing it soon. But anyway, glass frits are popular for non-aqueous. For example, a lot of reference electrodes use like ceramic or polymer frits. And those are not, it depends on the solvent, right? But like typically aqueous is great and non-aqueous can be tricky. They can kind of like blow through those frits pretty fast. So all I'm saying is that if you have like whatever your standard non-aqueous kind of reference electrode setup you have in your lab, if it tends to leak, you know, with non-aqueous solvent a lot, Alex's suggestion is really, really good, but you have to be careful if it's leaking stuff fast and you're putting ferrocene in your reference compartment, but it's leaking really fast. Well, you might as well just add it to your, it's just going to make its way in. Right. So if you have a well-isolated reference electrode and you can keep the ferrocene in it or use a salt bridge or something like that, then that could be a really good solution potentially, I think. Yeah.
All right, moving on, we have AJ Pradhan. Why is ferrocene methanol solution changing color and giving lower CV response after like just a month, even when refrigerated? I thought it was supposed to be stable electroactive substance. I've used a little bit of it. So this is also very specific. Oh wait, I'm using the silver wire paste from the connect. I'm using silver wire, silver paste for connection. I don't know, connection to what? I'm thinking the silver paste is contaminating the solution, but I filter out the solution after CV, but it's still the same.
Like when they're using the
ferrocene methanol?
Yeah, and then during the test, there's the silver paste. So thinking, is there contamination from the, you know, logistics of the connection that's causing it to turn blue, I guess you said? Well, I have no idea. I don't have anything to.
Yeah, I mean, ferrocene methanol, I'm imagining is orange in color. Maybe you're seeing a change in the color. That's my guess. And
is it supposed to be refrigerated? Is that a thing? I have no idea.
I'm actually not so sure. I haven't used that much. I used ferrocene methanol like maybe one time. I mean, but most people use something like ferrocene methanol if they want to do ferrocene cyclic voltammetry in like water, right? Because like there's no reason, like ferrocene methanol and ferrocene by themselves are not interesting molecules, but people want to use ferrocene methanol because
for
aqueous systems, because it's also like, because ferrocyanide can stick to the surface and ferrocene methanol is close enough to ferrocene. So you wouldn't need to necessarily use a silver wire, silver paste. But one thing to be curious about is if silver wire and silver paste is if that's your reference electrode, it doesn't surprise me that you're getting a different redox potential. There could be drift. That could very well be happening. That's just a guess, only based on what you've mentioned.
But I don't know why it would be.
Why the color would change has to do with, you know,
so obviously some chemical, chemical. Yeah, process. There's got to be some chemical process happening. I don't know enough about I've never used ferrocene methanol. I really don't know.
Yeah, no, me too. So sorry.
Yeah.
If you want to give us some more details, but also like, I don't know, take a UV-vis. Also let us know what's your electrolyte, is aqueous, non-aqueous system, that kind of stuff. So, but
yeah, I mean, yeah, but I guess that what you just said at the end there was you might be able to do like some UV-vis or like IR spectrum, like like ATR on it, like put a drop on if you have like an ATR FTIR. Put a drop of
down.
it when you first make it, get a spectrum, and then after it's been sitting in the fridge for a while and change color unexpectedly, get a new ATR FTIR spectra. I've done ATR FTIR, so that's the one that comes to mind for me. UV-vis, really, almost any spectroscopy, right? You might be able to figure out like that's how you determine like, oh, an OH bond will make, show up at this wave number or whatever. And so maybe you'll be able to see like, oh, I've got a wave number that corresponds with whatever type of characteristic bond. And so, maybe this kind of, maybe you'll be able to,
it's like disappearing because some bond is degrading, and you wouldn't know. Methanol just all of a sudden pops up, a methanol peak that's not connected to your. So
maybe you can get an insight into the like decomposition that might be happening. Let's see. Ramachandra has a question next. We're getting close to the end here, so we'll try to wrap it up if there aren't any more questions. But what if the surface of the working electrode is not plane enough? Does that impact the factor of resistance?
Yeah, your working electrode is basic. It's basic plane. You plain working electrode.
Yeah, you're not interesting. You're
not
so
interesting
plain
enough.
Why don't you get interesting electrodes?
I think maybe we need a little more information. But
what
plane, like what does plane?
Wait, not plain enough.
It's not plain enough.
So it is interesting.
Or maybe are you referring to like plane as in like just flatness? Like it's not flat.
Oh,
enough.
Is
that what you're? Yeah, maybe a little bit of
plane. Yeah, maybe. Yeah. So the way plane that you spelled it, PLAIN, would mean like boring. Right. Plain as in flat would be PLANE.
Like my water has a very plain flavor.
Yeah,
it doesn't have any flavor.
I didn't add any sugar to it.
Yeah.
But it's very flat surface of this
it might be
table. So
that could be.
Anyway, I'm not
just
sure.
A little confused. Sorry.
What you mean here. I think we'd need clarification to answer that one for sure. But I see your next question was, can you suggest possible pH neutral electrolytes to study redox reactions?
KCl.
KCl is easy. Basically, salt. If you can't handle chloride, perchlorate. I know sometimes perchlorates are not advisable for certain reference electrodes. But perchlorate, like sodium perchlorate.
Sodium nitrates
are good.
Are relatively good.
But perchlorates are really good. Apparently, perchlorate as an anion does not absorb at all on working electrode active sites. So that's why people sometimes prefer ClO4 minus, I think, perchlorate, like sodium perchlorate. So that is sometimes recognized as a good one. I think that's neutral anyway. Like that's not the conjugate, like the you don't want to, the conjugate of a weak acid can be slightly basic. So I think it's mostly neutral. It might be slightly basic.
So any conjugates of strong acids and strong bases will be so weak, by comparison that they shouldn't affect the pH.
So I think perchloric acid is pretty strong, and that's why it's okay. I think that's right.
Perchloric acid.
I'd have to look up stuff just to remember if I'm not totally off base here. But nitrates are pretty good, probably.
Sulfates,
nitrates, and maybe perchlorates too.
Be pretty good.
KCl's probably okay. I mean, people do stuff in NaCl and KCl too. It's just that chloride for like, I know for like platinum, it's bad. Chloride can adsorb to active sites and sometimes reduce the effectiveness of stuff. And so sometimes people are trying to avoid chloride. So that would be the only case where you wouldn't want to use something like KCl.
What could be the?
Go ahead.
I was just going to read Ramachandra's next question. What could be the relationship between charge transfer resistance and concentration of analyte?
There wouldn't be one.
There should not be one.
The concentration of analyte should be impacting your IR drop uncompensated resistance, things like that.
The current that you're getting.
Yeah, the charge transfer resistance would be more of a function of the potential that you're applying.
Yeah.
Of your electrode. I wouldn't. I mean, you may end up with an ancillary kind of relationship, but I would not expect a correlation causation type of thing between charge transfer resistance and analyte concentration. Those should not be heavily linked in the way that you might be thinking. Let's go back up here to Klaus. What measurements can be done to investigate CO2 reduction?
Cyclic voltammetry.
Yeah. I mean, really any of them that we've talked about, cyclic voltammetry, chronoamperometry, EIS, you're going to be polarizing your electrode at a, negative potential, whatever it happens to be, depending on a million factors, your reference electrode and your, pH and all that kind of stuff. But reduction is a negative potential, process. And so you're trying to reduce, CO2, typically either in a gas form, obviously, or bubbled in solution or something like that. And you're going to do any of the kinds of tests that, one would do for almost any, start sweeping LSV or CV, sweep negatively and measure the
onset potential for CO2 reduction. And then when you add like a catalyst or something, does that onset potential decrease or change? Is it, you're decreasing the over potential? Some people, as you said, do like a bulk electrolysis experiment, and they're actually they're collecting coulombs of charge passed, and then they're measuring on the GC how many moles of quote CO2 reduced product that they're generating. So those are just a couple people used to study.
Cigar's question next, I guess.
Yeah, cigar.
Maybe one more, and then I think we'll wrap it up.
Yeah, I think we're almost done with all the questions. So, do we have any technique to determine the compatible? I think it's compatible applied current density of our electrode in supercapacitors, or maybe compatible.
So, I'm pretty sure you mean compatible, but I don't really know what compatible means in this sense. I mean, if you're talking about applied current density to, I don't really understand the question. Supercapacitors, usually you do stuff like electrochemically. If you have a supercapacitor material, sometimes you do this like experiments where you do CV back and forth over a very narrow window where it's only non-Faradaic stuff happening, and you increase the scan rate. So you'll get something like this. With a supercapacitor, you'll do a CV, right? And normally you do a CV and you get, peaks. These are like Faradaic processes, but for a capacitor, you're looking for non-Faradaic stuff. So you're not looking for any peak.
He's saying during charge discharge. Let's see.
Yeah, so maybe this isn't what we're talking about. Any technique to determine the compatible applied current density to our electrode?
In supercapacitors, applied current density. Applied current density.
Technique? Are you trying to find the current density, or are you trying to figure out what determine the applied current density
to our electrode?
Well, you have to know the capacity to know how much current to apply, basically, right? Like
current density in this case is like current per area, surface area,
or per mass. I guess either, right? I mean, it could be either. I mean, current density. Yeah, I'm not sure whether.
Yeah, so that's
what you mean.
But I think your technique, what you're describing, will help answer.
Yeah, I mean, you're trying to determine. So if you're doing CV at different scan rates, you're going to get sort of envelopes like this, right? You scan faster, you get, and then I always mess up the equation exactly, but right, the current that this makes here is proportional to the scan rate and the capacitance, and so you can get if we apply the low current density, the desired potential is not. It's probably because you need enough. Either it's too slow, or it's like so the capacitors are going to be, I think, a little different than other storage devices. You probably need to apply enough I think maybe the problem is it's really like the potential's not achieved. It's because it's probably too slow. So, I mean, what you're talking about is like, what's the capacity? Like if you have a super capacitor that has like 1 amp hour of capacity, which is, or like whatever the coulombs is like, okay, it's like 3,000, whatever. I'm trying to write numbers here. Well, I think like 3,000 coulombs of capacity of charge it can, deliver or needs to be charged up. And you're applying a current of like a microamp. Okay. Then just making up some numbers. Let's say you have 3,000 coulomb capacity. Sorry, I don't mean the scan rate in CV, but the current in charge. Yeah. Okay. So this is what I'm talking about now.
Okay.
The current.
Yeah.
So, okay. So if you have like 3,000 coulombs of capacity of your, whatever, your supercapacitor, and you're applying a microamp, this is just one, extreme example, right? Over,
take you forever.
It's going to take you forever. Right. Exactly.
Yeah.
So times 1 second gives you 1 microcoulomb, right? That's just simple math, right? So 10 seconds gives you 10 microcoulombs. So how long until you get to 1,000 coulombs? Well, 10 to the 6 gives you 10 to the 6 seconds gives you 1 coulomb. And then 10 to the 9. So how long is 10 to the 9 seconds? Anyway, that's a couple of years. Okay. The point is, you might just be using too low of one. So the answer to your question may be that you need to know the capacity to figure out what an appropriate applied current is, or current density, so that you actually charge it up. Almost, what you might see is that the voltage isn't even like rising at all, because it's just too slow. It's like it is rising, but it would just take an absolutely ridiculous amount of time. And so if you don't know what the capacity of your supercapacitor is, you might have to just do some capacity determination kinds of tests where you apply larger and larger current. Like if you're applying 1 milliamp and it's taken forever, then you might have to be like, all right, well, I'm going to apply 10 milliamps. All right, I'm going to apply 100 milliamps, and measure how long it takes to get to the upper potential. And then you get a measure of your capacity, right? If you apply 100 milliamps and it takes 2 hours to get to whatever your upper potential is, well, then you have an answer, right? That's well, it's 200 milliamp hours, which is however many coulombs. You got to multiply by 3,600. So you'd have your answer, right? Of your capacity. So you might have to determine your capacity first, because only by knowing how much it can take can you know how much you should apply. Otherwise, you might just be applying it too slow.
We apply over current, the resulted capacitance is very low.
If you apply over current resulted. Well, yeah, because if you apply too large of a current, your performance will be poor if you try to charge or discharge way too quickly. Now, a lot of what I'm describing is true in the realm of batteries, and I'm not perfectly well-versed in supercapacitors to know if this is all exactly applicable to capacitors in the same way it is to batteries. But for example, if you try to charge and discharge a battery really, really quickly, it will not perform very well. If you try to do it more slowly, it performs better. Capacitors, I know, actually are a little bit different. They're in many ways designed for a very quick charge and discharge. So the two possibilities that I would say to this information, without knowing much more specifics, are that either you need to find the sweet spot. Well, you've said too high, it's not good. Maybe otherwise it's too low, it's not going at all. Maybe you need to find the sweet spot somewhere in between. If that's not the case, it might be that your capacitors is there's some structural problem, some chemical problem. There might be a problem with your device itself, maybe. Otherwise, I don't know if I have enough knowledge to answer more specifically. Like I said, most of my knowledge of the storage devices are like fuel cells and batteries. I don't know if this is exactly the same logic as it relates to finding that right kind of charge rate or whatever for a supercapacitor. I think we're just about done here. This was
done. Oh,
I mentioned Nafion. Chempor says, can it be used effectively in a divided cell that has no real use or need for ion exchange properties?
probably.
Probably.
Still can allow ion conductivity, and that's all you really need.
Yeah, I think so. Ultimately, you need to have something that allows the passage. Well, a divided cell like necessarily needs ion exchange properties. I think what you probably meant by your comment is that doesn't have like specific need, like protons or whatever. You just need to be able to like, I mean, a divided cell has to have some ion exchange properties, otherwise it won't work.
Yeah.
But I think probably the answer is yes, but most likely you'd still possibly struggle using like Nafion with an alkaline system. It's just not meant for that. You know, like Nafion is like a phosphorus or sulfur. It's this polymer structure that is designed to shuttle protons. So I don't know if it would work perfectly well in all situations, but I do think it's pretty like cheap-ish, like Nafion is. It's pretty ubiquitous. So what I would say to some extent is like, it might be accessible enough that you can try it, even if like, well, it might not work, but it's probably not like going to break the bank to get a thin piece of Nafion and try it.
Yeah.
Thank you very much, Cigar.
Yeah. Thank you so much. I don't know if we were able to answer your question exactly, but we
doing our best here, but certainly
donation.
appreciate your contribution here. You're
thanks for the super chat.
Kind. I think Vinod will try to answer this last
question. Yeah, I think so. Just how to calculate the current. So Vinod asks how to calculate current density of linear sweep voltammetry averaged by electrochemical surface area. It sounds like you answered the question itself. But if you want, I can just show you like when you're doing, let's see, if you're doing linear sweep voltammetry and you have, let's get anode together. If you're doing linear sweep voltammetry and you have something, you know, you get your CV that looks like, you know, it's like this, you know, some voltammogram. Again, now I'm not making very good ones, but you have current here and you have voltage. And if you know what the area is, which you stated, all you need to do is take the current and then divide it by area, and that will give you current density, or J. And so that's it. And basically, you would just take density. Can't draw. Can't write with this. But that's all you do. You just take the current, like, because that's what the potentiostat measures, is just the total current. And when you know the area, you just divide it, and that will give you the current density. And then you can, and then all it does is just shift this by a ratio, and then you get current density versus voltage.
Yeah, many people prefer to report current normalized by either the geometric or the electrochemically active surface area in that way.
Yeah.
So it's really just, honestly, it's a preference.
Yeah.
But I think we're going to wrap it up there.
Yeah.
I think we've got to all the questions. We do try to get to everybody. If we missed you, we do apologize.
Yeah.
If you are watching this later, and you've made it this far, thank you.
Yeah.
But feel free to leave a comment and see the timestamps and the timestamps in the description for any parts that came before this as well. And if you leave a comment on this video, we'll answer it, you know, offline, or you're welcome to join us on future live streams. We're sort of trying to keep a running Fridays at 1 p.m. Eastern time in the US as our live stream appointment, I guess, on YouTube. So if you prefer to ask another question live, join us next Friday, I suppose.
Yeah, I think you'll be doing that. I will be at the Electrochemical Society meeting in Boston So if you're there, if you're at the Electrochemical Society meeting in Boston next week,
Go say hi.
you can come and stop by the Pine Research booth
That's
and
right.
say hello.
Alex exists in real life.
That's right.
I don't. I'm only an internet person.
Yeah.
So no, but I won't be in Boston. But I have a few other meetings that I'm going to later. Yeah. So if you are going to be in Boston, go say hi to Alex, and I'll join. Well, I won't join. I will just do the live stream by myself next week. It will be lonely and much worse without Alex here. But sorry, how dare you ditch me?
It happens. We've done a few solo live
Yeah.
streams, but and they've
Try to
seemed
keep it going
pretty
here.
well.
Yeah, as the summer goes on, we may have weeks where we're not able to do this, but we will try to do this every week when we're able to. And anyway, thank you everybody for joining us, and I hope everybody has a great weekend, and we'll either see you next week or in Boston or at a future date. So
Yeah. So yeah,
take care, everybody.
bye.